and welcome to another episode of Hi I Like Maths, which is all about how mathematics can improve our mental and intellectual abilities. This is not a technical show, which means we won't present mathematics formulas or abstract stuff. Rather, we talk about challenges, problems, solutions, research, and discoveries in the world of mathematics and its applications. My name is Linda. I'm the host of the show. I'm applied mathematician. I completed a PhD in it. I'm also a maths educator and the founder of Bungee Pie, which helps children learn mathematics using storytelling, animations, and real-life applications. It also helps maths teachers and schools develop numeracy, problem-solving skills, and critical thinking of their students. Today I'm honored to have Dr. John Adam, who is super duper well experienced and knowledgeable applied mathematicians. Believe me, he is impressive to talk about patterns in nature. So hanging there, he will show you so many pretty cool photos and tell you how you can use maths to find patterns in them. Let me give you a brief introduction about him first. Dr. John Adam has been Professor of Mathematics at Old Dominion University, located in the coastal city of Norfolk, Virginia, United States of America since 1984. His PhD from the University of London was in theoretical astrophysics. As an undergraduate, he was exposed to a concentrated diet of Monty Python's Flying Circus, and he has never fully recovered from it, even at his advanced age. His first introduction to the United States of America was through the humor of the Far Side cartoons by Gary Lawson. He has broad interest in mathematical modeling and applied mathematics. He is a frequent contributor to Earth Science Picture Day. In 2007, he was winner of an Outstanding Faculty Award for the state of Virginia. In 2012, he was a recipient of a Cole Allendefier Award from Mathematical Associations of America. He has published approximately 120 scientific papers and has given over 180 presentations to professionals and university groups. He has published several books, all published by Princeton University Press, and he will talk about it during his presentation later. Dr. Adam also enjoys writing resource articles on applied mathematics for teachers. Isn't that impressive, really? A long-time contributor to the world of mathematics and its applications. Welcome to my show again. I'm quite honored to have you. When I was going through all your background and what you have been doing in the space of mathematics education, maths modeling, applied mathematics, and all of the crazy things, I was so impressed. And I was thinking, oh my God, I really appreciate the fact that we have this social media, LinkedIn, and this pandemic to really make us closer to each other and find quite amazing, impressive people. And I would like to thank you for accepting to be part of this show and give us a bit of insight of some of the works that you have been done. And I'd love to invite you back again to talk about more interesting things because I'm pretty much sure you have a lot to say. So let's start with the first question, which is about, well, you need to share a little bit about yourself. So what did you want it to be growing up?
Well, that's a great question because at the age of around 13, I came across a book called The Observer's Book of Astronomy by Patrick Moore, one of a series of observer's books on different topics. In nature, butterflies and flowers and so on. But I devoured this book, so to speak. I really got interested in it and so excited. I wanted to be an astronomer.
Oh, wow.
Okay? And I grew up, my parents it was a very working class home. We never owned a home of our own. My parents didn't have a lot of money, but they were so excited that I wanted to do this, that they actually bought a small telescope for me at great expense.
Wow.
£25 then, which was quite a lot of money, a beautiful brass telescope, and you'll see a picture of it later.
Right.
And when I was about 14, the algebra teacher at the school I was attending, Henley-on-Thames Grammar School, was going around the class asking us what we wanted to be. And I stuck my hand up and said, oh, an astronomer, sir. And a very worried look came over his face. And he said, Adam, because they referred to us by our last names.
Yeah.
Adam, even observational astronomers need to know a lot of mathematics.
Wow.
You are bottom of the class in algebra.
Right.
Now, he was being realistic. I had the choice, I suppose, at that time of just getting discouraged or just working my tush off to just keep going. And I did that.
Right.
I would love to have had the opportunity to go back and after I got a PhD in theoretical astrophysics.
Right.
But I never did see him again. But anyway, so that's really propelled me. I just kept working and working and working at it. I wasn't the best in the class, obviously being bottom in algebra, but I pulled myself up in that sense.
Right. I would just from what the look of what you've done so far. I know you're so passionate about this stuff you've been talking about, but I would like to actually ask this question: is there anything else you're passionate about? It's just all the maths and life.
Well,
maths in life is just your things.
I feel like I can only do one thing quite well, and this is it. But I would say that what's underlied my teaching in the last, I suppose, well, since I had open heart surgery, actually, and a heart attack in 1996, since that time, I've been fascinated by what I can put succinctly as the beauty of nature as revealed by mathematics and the beauty of mathematics as revealed in nature.
Right.
I've got some pictures here of just plain old perspective. This is in the city where I live in Norfolk, Virginia. And I like to joke with my students and say, geometry is amazing. It applies the world over, not just on mountains, not just where I live, but in the Netherlands. You see again
this is very interesting.
And this is an example of something called the spectre of the Brocken in the Brocken Mountains in Germany. In medieval times, so I'm told, individuals on mountaintops, when there was a cloud bank ahead of them and the sun behind them, would sometimes be frightened by images of giants, big shadows, and the giants moved. And what it is essentially their own shadow projected on the cloud bank. But because the shadow's so long, then you've got these distorted images, elongated shapes, and sometimes even glories, those colored concentric rings around the head of the observer. And it occurs, you can see it not just there, but if you're on a mountaintop or a hill or in a hot air balloon or something, if the conditions are right. So we move on to something a little different, connected with something called the Fibonacci sequence. And I don't have time to go into all that today, but I will share with you one little mathematical aspect that's related to the distribution of bracts in pine cones and pineapples and seeds in sunflowers and so on. I'm sure many of your viewers will be familiar with the Fibonacci sequence.
Yeah.
The pineapple, of course, and an open pine cone. Actually, I should have put a picture of a closed one, but they open in the heat. In fact, you can use it as a rough guide to the temperature if you know what you're doing. This is the spiral patterns in a daisy head. I don't know whether I have a picture of sunflower on this one. These are helices, of course, a sort of three-dimensional spiral. I'll be talking about the golden angle in connection with the distribution of leaves in a lot of plants. And I'm going to sort of run ahead here, okay, and then go back to those slides.
Sure.
If you take a circle, subtending an angle, of course, of 360 degrees or 2 pi radians at the center, and you were to pose the question, what is the angle B, let's say, such that the ratio of the larger angle A to the smaller angle B is the same as the ratio of the whole circle to the larger angle. So in other words, 360 over A equals A over B.
Okay.
When you do that sum, you get a quadratic equation, and it turns out approximately the smaller angle is about 137.5 degrees, and it's called the golden angle, just like the golden number when you do the same thing by dividing a line into segments such that the large part to the small part is the same as the ratio of the whole to the large part. So this is complement 222.5 degrees. Now let me go back. I'm just going to go forward. It's an angle that socially responsible leaves appear to be fond of using. So from 1 to 2, say what 1 is the oldest, then to 2, about 137.5 degrees, 2 to 3, 3 to 4. And you can see if that angle were 90 degrees, then you'd get 1 here, 2 here, 3 here, and 4 here, and they would stack up above each other. And of course, you do get plants like that. So this is just this is just one type of arrangement, but it does seem to maximize the opportunity for leaves to get sunlight and moisture.
That's very interesting.
Back to pictures that I take often have my shoes in them. This of course is some kind of cactus, and I haven't actually bothered to measure these angles because you've got to find out which leaf preceded which leaf. It's a little more tricky, and cacti are prickly, so I gave that up. But here's another example of some common weed actually I took outside my house. So you can probably do the same thing there if you had the intent. So anyway, that's golden angle. And by the way, this is a picture. Looks like a mouse has been nibbling this, but that 137.5 degrees, if you actually change the angle to say 136 or 138 or 139, you don't get this nice packing distribution of seeds. Okay, you get some spirals appearing eventually. It's a bit of a jumble and then spirals. So this does seem to be a very useful space filling angle. And there's been a lot of research on that, on the Fibonacci sequence and the subject of phyllotaxis, which is the arrangement of seeds and leaves on a stem. Now again, moving on, we have spider webs, which have these polygonal features, and they're not regular polygons, of course, but that's an amazing one I took in my backyard. That spider was capable of dragging people into the net. It's huge. Here's another one.
You have them here as well.
I'm a bit of an arachnophobe, but I'd overcome that when I take pictures.
Yeah.
And of course, we're familiar with the bilateral or mirror symmetry in butterflies and moths, and they're just beautiful. This is a swallowtail that visited my garden globe.
Wow.
This is a picture of a blue morpho butterfly, and it's not actually, the wings are not that color. That's just an interference phenomenon, just like when you've got a patch of oil or petrol or gasoline on a puddle or something. And so you've got interference between the different layers. Here in the case of the butterfly or the moth, it's the chitin cells that are sort of stacked. And again, this is a close-up of that kind of thing. Now this moth was about 5 inches across and visited my office one day, and it's actually attached itself to an unopened pile of reprints of papers that I had.
And it's pretty one. It's very pretty.
It's pretty, yes. An owl moth, I think. I'm not honestly sure. Anyway, a very intelligent moth, as you'll see, because it's sitting above a book on advanced calculus and studies in mathematical biology, partial differential equations, ordinary differential equations, and then Courant's books on differential and integral calculus. So highly intelligent moth. Clouds can form wave-like billow and lenticular structures with well-defined wavelengths, just like ripples flowing around associated with rocks in a swiftly flowing stream. And now these
wow, look at that. Oh
you
my
know, some
God.
piles of plates, flying saucers, UFOs, and it's to do with different levels of humidity in the atmosphere. And as a wave, usually invisible, acoustic gravity waves go over mountains and hills, they can set the air into oscillation. And in these cases here in particular, and this one, and the bottom right, what's going on is that all sorts of wavelengths are being generated, but only those waves that are moving upstream at the same speed as the airstream is moving will stay stationary relative to the mountain or hill. They can stay like that for hours. It's quite fascinating, and it's the same kind of mathematics associated with waves and ripples in a stream. And I think I have a picture of that coming up. Oh, this was from Earth Science Picture Today on
I really like it.
2017. Yes, and your readers can go back and look at all those. Here's again a twig, you see, in a stream, and you've got these ripples ahead of it, and you actually have longer wavelengths behind it. So these are actually induced by capillary surface tension. They're called capillary waves, and there's gravity waves behind, but it's the same kind of phenomenon. In fact, you can get breaking waves in the atmosphere. If the conditions are right, you can actually see them, but generally you don't see them, but you feel them if you're in an aircraft. It gives rise to clear air turbulence. It's actually called the Kelvin-Helmholtz hydrodynamic instability. And they do go the other way as well, as you can see.
Wow.
And you can find a lot of exotic examples of these breaking waves on the internet. Mirages. We're coming towards the end here, I think, but I like to say that a mirage is an example of non-Euclidean geometry at work.
Wow.
We're all familiar with the road puddle. It's called an inferior mirage, not because it's in any way irrelevant or not interesting. It's inferior because it lies below the thing producing it, which in this case would be a patch of sky. So that for an inferior mirage, this is greatly exaggerated, but the light path is curved this way. The reason being that there's a nice theorem, which I call the mirage theorem, which says that light will bend towards, is concave towards regions of higher density. So when you've got a hot road, the density of the air above the road is slightly less, very slightly less than the air above it. And so the light from the patch of sky or a cloud bends, again, highly exaggerated, this way. And so you, the observer, sees the patch there.
Wow.
Now, superior mirage, when you've got a cold surface, denser air over the surface of the ocean, say in winter, then you can get the curvature this way. And so you look and see the iceberg sometimes, or the ship, sometimes upside down. It depends on what the levels of atmosphere are doing. If there's various density distributions that give rise to this, and you can get some quite amazing pictures. You can sometimes see from around the horizon. This is the inferior image again, inferior mirage, and I've got a sequence here of distortions from I'll go back, superior mirages, where you've got things, look, it's a floating yacht. Isn't that amazing?
I like it. Look at that.
Yes, so that would be a fun ride. And I'm sorry, this is all sort of different things all patched together, but more polygonal patterns in mud cracks. There's my ugly foot, which you might see a little later. Look at the scales, the different scales here.
Yeah.
I put my foot in that deliberately for scale, but you can see some are going down to the centimeter.
Little, and
this is, I like to say this is a picture of the neighbor's dog after a long drought. A funny looking animal, I never liked it, but they're just mud cracks, of course. And these are polygonal ice patterns I took while walking around a body of water near where I live one cold January morning, and not regular again, but also on the tarmac atom on the surface of roads.
Mm.
And some of these cracks are at right angles. So it's interesting, depending on the type of material used, you can get different shapes. And of course, these aren't cracks, but this is patterns on the rear end of a giraffe. And here we've got patterns, almost regular hexagonal patterns on the salt flats. And here is the Giant's Causeway. Again, many of these are regular, close to regular hexagons. Giant's Causeway in Northern Ireland, caused by rapid cooling of columnar basalt. And it's the same kind of geological structure as occurs in Devil's Tower, Wyoming. And if you've ever seen the movies Close Encounters of the Third Kind, that's the mountain that appears there, and it has this kind of pattern. Hexagons, again, here's a worker bee taking a break from its work and creating actually hexagonal patterns in the honeycomb. Another fascinating thing is waves on the surface of ponds and puddles. This is an idealized version, but they spread out in a circular fashion. Here's a moth, unfortunately dying, struggling, it's going to drown, but you can see some interesting patterns there. It was very cruel. It was taken by a friend of mine, so blame her. Everybody should have their own wave maker, right? Something, look at all the fascinating patterns there. I'm going to say something about this in a minute. Now, let your viewers have a look at this. One of these figures represents the pattern of waves on a puddle after a raindrop has fallen on the surface. And the other corresponds to the wave pattern after a small rock's been dropped in it. And what I usually do is ask people to put their hands up if they think, well, which one do they think is the puddle pattern? Is it the one on the left or the one on the right? In other words, raindrops fallen on a puddle. And you can go out and check this after a rain shower, but 90% of people I've found over several years doing this actually, well, think about it. I don't want to give the game away too soon for your viewers, but 90% of people say the thing on the right is the puddle, and it's not. This is not. Now, what happens is, very briefly, and you can edit this out should you wish to, these shorter wavelengths are caused because the raindrop is small relative to the rock, say, and the wavelengths are comparable to the object producing it. Now, because these are small wavelengths, the speed of the waves is inversely proportional to the square root of the wavelength. So the shorter the wave, the faster they move out. So you have a sequence of increasing wavelengths as you move in, and there's this region of calm which spreads out from the center. Whereas longer waves, like it would appear on the ocean, for example, but on a pond when you drop something large into it, like a calculus book or a math professor, then the speed of the wave are proportional to the square root of wavelength, not inversely proportional. So the longer waves move out faster. So that's worth looking at. And in fact, here, this is my grandson, Felix, used with permission. He looks terrified, poor little guy. But look, here's the drops splashed. You can see this pattern here. Yeah. Right now, was so terrified, he's never had a bath since, and he's 10 years old now, so we never go and visit him because it's just too smelly. All right, now, ship and duck waves have a characteristic wedge shape angle, nearly 40 degrees in deep water. So whether you're playing with your rubber duck in the bathtub, or you're looking at a real duck on a pond or an ocean-going liner, provided the water is deep, and I'll explain what that means, you get the same pattern. By deep water, I mean that the wavelength of the waves is small compared with the depth of the water, okay? So you can get these kind of wedge-shaped patterns here. This is a better example of it. Feathering, and again, quite simple geometry can explain why this happens, although the mathematics can also get very sophisticated as well. Right. So I promised to show my ugly foot again. One time visiting a national park in New England. It was pouring with rain, and we were stuck on a balcony somewhere. So I decided to stick my foot out and take a photograph of the raindrops falling and ask my students to estimate the speed of the rain from that picture.
Oh, wow.
Now, of course, you know, because, I'm not a giant, most people should have a good idea of the width of that foot, you know, within an inch or two. And I think I gave the shutter speed. And so I did the sum here, and I won't dwell long on it, but you can see, so I gave the width of my sneaker, and by comparing that with the length of this, you can do a simple sum that comes out to be about 20 miles an hour. But of course, I couldn't hold my leg fully horizontally because I'm not a ballet dancer. So there was a certain amount of perspective there, the angle of dip. But anyway, and I point out, for those who don't have access to my foot, anything in this range is reasonable. And that turns out to be about the right order of magnitude for speed of rain.
Interesting.
Okay. Symmetries, pentagonal symmetry in this vinca, I believe it's called. I basically know two types of flowers, roses and not roses, but this I think is a vinca, and this is, I forget what this is, but again, lovely symmetries here.
Wow.
Symmetry. I love this, you know, the great surface area to volume ratio here, very tiny volume, but huge surface area for collecting moisture in a very arid part of the world.
Yeah.
There's some bilateral symmetry here, the comb for the, just to show the scale. It's very important to have scale in these pictures. I love this. This is about an inch across, or 2.54 centimeters approximately.
Oh, wow.
Now,
look at that.
What on earth is going on here? Is this an aerial photograph of river drainage patterns? What's going on? What do you think it is?
Oh, it's like painting.
Yeah, it could be abstract art, isn't it? Yeah.
Really?
What it is pollen patterns on puddles, and forgive the alliteration, but each region there is about 18 inches to 2 feet square. So I was walking to work, and it'd been a rainfall, and there'd been a lot of pollen around. So cars instantly went from black to yellow with all the pollen on them, but once it rained, they went back to black. But these were intricate patterns.
Yeah.
And as I was walking to work, I kept stopping to take more and more pictures. So that's absolutely fascinating. That's one of my favorite.
This is really cool. I thought that is like an abstract painting.
Yes.
Oil on canvas.
I published a lot of these pictures on Earth Science Picture of the Day, and I'll give the website link to
sure.
that.
Yeah, for sure.
Now, is this Winnie the Pooh asleep or pregnant? I don't know. This is a hummingbird. I just took a picture over
wow, this is
house
so
and rotated
I really liked it.
Yeah. This is a baby alien. Remember E.T.? You know, here's a big one looking at another one. In fact, I've got a better E.T. Here we go, E.T. Happy little dog. Here's his eye, his nose, his snout, his ears, his legs, his tail. And I had this published in an exotic book called Clouds That Look Like Things, published by the Cloud Appreciation Society, which is real, by the way. So this is a skeletal waiter serving a pizza or throwing a frisbee. This was taken in Alberta, in Canada.
Right.
Here we have another dog jumping over a tree. Here's his tail, here's his head, here's his feet. Okay. A nosy neighbor. She's got her hair up in a bun, and she's peering over the fence, you know, and I rather like that picture. This is not a cloud. I have to tell you, it's not a cloud. I call this the Loch Ness Monster. Twisted trees and symmetry. Now, I took this picture.
This is in the water. This is a reflection in the water, is it?
this is sorry, what did you say?
It's like a reflection of a tree.
Yeah, but it's interesting, the waves seem to be going the wrong way, don't they? I liked it.
Wow, this is so nice.
I posted this on Earth Science Picture of the Day, and my first explanation was that I happened to be in the vicinity when a supernova exploded in our galaxy, and it caused fluctuations in the space-time continuum, and I just took a picture of the tree as that pulse passed through at the speed of light.
Wow.
Of course, what actually happened was that I saw the reflection of the tree in a pond. I threw a stone in the pond because I always like throwing stones.
Oh, got it.
And then I inverted the image.
Wow.
And after that,
Very
I
cool
noticed,
idea. I like that.
you see, because here we have the rays going the wrong way, because the radius of curvature, as the curvature should get less as the radius increases. But here we have, everything's the right way up. So it was that reflection and then inversion. And I noticed a sign which said, "Do not throw stones." It was too late. Okay, so nearing the end. As a cure for insomnia, here are some of my books. Mathematical Nature. My first book was Mathematics in Nature, Modeling Patterns in the Natural World. And in the cover of the hardback version of Mathematical Nature Walk, you can see my telescope.
Oh yeah, the one you talked about right at the beginning.
And you can see I'm also an expert in levitating things, so that's a bonus. It took me a long time. They do say that before Newton invented gravity, everybody levitated. With my colleague Larry Weinstein, we wrote Guesstimation: Solving the World's Problems on the Back of a Cocktail Napkin. And here you can see John, the human dandelion, and Larry. We're holding hands for electrostatic purposes only. He has his left hand on a Van de Graaff generator.
And, so this is not a Photoshop photo.
No, it's real.
Wow, this is so cool.
Absolutely true. Yeah.
God, I love that photo.
And this book, I thought would sell a lot of copies because of the title, X and the City, Modeling Aspects of Urban Life, but it never did. So I think people probably took it off the shelf and thought, oh, that looks interesting, opened it up, saw the mathematics and put it back. Anyway, by the way, I've never seen the show Sex and the City, but I do know that it caused quite a lot. But here you see X refers to all sorts of different things. Each chapter deals with X as, say, the average speed of traffic in a city, or various things. This is my most recent, which is a more advanced graduate level book, Rays, Waves and Scattering. And you see the picture?
Yeah.
You see the picture.
It's really
and my wife's suggestion is that we use it as a doorstop. Okay, so it's a big, heavy book, like a brick. Okay, websites you should visit regularly. Optics Picture of the Day, OPOD, and associated with that is called, well, actually the main site is Optics Picture of the Day, but you will find different pictures put in over a regular period of time, submitted by people to Dr. Cowley, and he will put them there with interesting explanations. And then Earth Science Picture of the Day, which is a wonderful site and very useful for educational purposes, because it's a project linked with the University Space Research Association, and they have a lot of links for students, for high school kids there. And I've published probably about 50 over the years, pictures there on that, and you can search for that.
For sure.
Now, our department website that I'll give in a minute has a link to 2 12-minute videos entitled Nature's Mathematics. In fact, only yesterday I had a nice email from a lady who had been watching it with her daughter, and the daughter was 10 years old and they loved it. So now the company that produced it is called Curiosity Stream, and they own these, so I can't share them except through the department website.
Right.
They've done wonderful graphics, even if you have to listen to me drone on in the background. And so if you go to the Old Dominion University web page, I should have put that, odu.edu. So that part, that's my email address, but the odu.edu would get you to the university web page, and you can find the mathematics department. But they've got the links to those 2 episodes there, and this is what the screen would look like when you get to that point.
Sure.
They're each about 12 minutes long. And penultimately, here's me outside John Adams Street in London. Now, I'd like to think that it was named because of me, but no, it wasn't. Named for a Scottish architect in the 1700s, I believe, or 1800s. But it's a very short little street. But I made sure to have my photograph taken there when I last visited London. My son, who lives in Chester in the north of England, northwest of England, he supplied me with a much improved version of this picture. And so that is, and as you can see, he has a lot of respect for me. And I think that is the end of the presentation.
Was really cool. I really enjoyed it. There are a few more questions that I would like to ask you.
Yeah, and I'll be brief.
Yeah. So tell me about some pain points of being a professional, successful person. So if there is any.
One of the pain points is that, just distress. None of my colleagues share this, over the increasing lack of interest or indeed knowledge of basic mathematics in the students that we see these days, on how mathematics impinges on their lives. And the number sense seems to be eroding. Students often, I think people in general, sometimes are more gullible. They're at the mercy of, hoaxes and conspiracy theories if they don't know how to do sort of back of the envelope guesstimation. Is this for real? Do these numbers make sense?
Yeah.
And that's something I think that we, should be part of a regular education. You don't have to have advanced mathematics to be able to do some order of magnitude estimates. So I have another talk which I taken from the book on guesstimation, where I give some examples of this. How many cells in the human body? What's the surface area of the human body? How many people are picking their nose at this moment around the world? And you can get an estimate of that. You can go from sensible questions to silly questions, but just using what I call applied arithmetic. So that's discouraging, although I am also encouraged when I see students who really do know what's going on and are curious and want to know more. And I think students like the 10-year-old girl I was telling you about, her mother was explaining how they do. She loves nature, and she loves mathematics, and she loves estimating things. I mean, that's wonderful. That's absolutely wonderful, and that's what I'd like to imbue in both my own grandchildren, but also children of all ages. You're never too old to enjoy doing this stuff.
Sure, yeah. People, thank you for listening. I hope you enjoyed it. Please support us by subscribing to our channel, High Alog Maths. Till the next episode, be a maths lover.